Normal faults are the principal tectonic structures in many of the world's sedimentary basins, and seismic images like this have provided the greatest insight into these fault structures. Their geometry, size and distribution. But if we were to understand the fault patterns properly, we need three-dimensional information, which means combining profiles like this with plan views, such as this. This is a map of a stratigraphic horizon showing its depth below the seabed. And the normal faults are the black strips where the horizons have been pulled apart. Some people call these fault loss or fault gap maps, and to understand them, let's make a physical model. I've got some foam that will represent the stratigraphic horizon, and we'll see through it, but to make the faults, I'm going to cut some slits in this foam horizon. So now, if we pull this horizon apart, we create gaps here and on the other fault here. So these are gaps in the horizon, they're fault loss. And a map that looks down on a horizon with fault gaps in it or fault loss shows us how the faults continue, it gives an idea of their length and also how they interact with one another. Just to be clear what these look like, let's just go back to the profile and add a stratigraphic horizon. If we strip away the faults and focus on the main offset, this is the gap in the horizon created by fault displacement, fault loss, equal to the fault heave. So if we go to a horizon map for this sedimentary basin, we're looking down on the faults. They're represented by these black streaks, and we can use this map to measure fault lengths and see how they interact with one another. The catch is to give insights to students taking a structural geology class, and especially to help them build confidence in interpretation of the structure of normal fault systems. Well, it's highly problematic using seismic imagery and data itself. To build horizon maps and fault maps, the basic input for this type of work could take even experienced interpreters assisted by modern AI technology many hours or even days to create a robust 3D map. In a structural class, we just don't have the time, and we don't necessarily want to spend a lot of time training students in how to use specialist software for a single task. What's more, many communities around the world don't have access to the technology at all. So, to meet the challenge and still provide a meaningful structural geology interpretation exercise, I've designed a task using, well, tectonic geomorphology. Google Earth has revolutionized the way in which we can share understanding of tectonic geomorphology. And we're just going to go to one small part of the world to understand normal fault systems. But where in the world are we going to play? Well, it's here, on the southern margin of the Red Sea, in the country of Djibouti. So this black landscape is formed by a very young basaltic lava flow, and it's this that will form our stratigraphic horizon that we can use to identify faults. So we can see the grain in the image here that's running north-south. Well, these are the faults. Now, in order to make best use of the aspect ratio of the screen, I'm going to rotate this image so that north's on the right and our faults will run in this direction, like this. So here are our faults. In order to get to this location efficiently, I find it useful to provide some navigation information to students, and I use the What 3 Words app that provides satellite imagery as well as very precise grids of locations, which we just get 3 words to find. If you pop those into the app, it'll take you into this image, and then you can use that to navigate back to Google Earth. We're going to just use a small part of the map just to get a quick insight into part of the fault pattern. The advantage of that is it leaves a great area outside this window that can be used to set further assignments for students. Okay, anyway, let's crack on and look at this map area. And we're going to use the ability of Google Earth to provide all sorts of perspective views that will give us 3D insight into this landscape. And we're going to compile our understanding onto a single base map. And I'm going to use some coloured pens as I go. Of course, we could also do it digitally by having another screen, but I find it really useful to work on paper, which gives you a quick insight at the same time. If you want to build a digital model, then of course you can then take your paper version and create a digital version from it. So let's zoom in and have a look at some of these faults in profile, so side on. So I'm just going to zoom in to a small part of this image. Let's spin it around first, so we're looking along the structures, and then we can just come in here and have a look. I'm going to zoom us right in. Okay, so now we're looking side on to a series of faults that are inclined like this, that have offset the black coloured top surface in here. So let's just look at an interpretation. Let's sketch a cross section with the basalt layer in green and the fault scarps, the gaps in this layer. So these are the fault losses. Bear in mind that there's uncertainty in this, caused by surface processes, in other words erosion and deposition, so that we may slightly overestimate the gaps, the fault heaves. But perhaps this isn't too much of a problem in this very young and arid tectonic landscape. So let's get mapping. We're going to trace out the top and the base of the escarpments, identifying the fault surface as we go, and we'll map them out fault by fault, compiling them onto our base map. Right, let's get a different view. So we've got the fault in profile view here. We can recognise the top of the escarpment here, coming around, and its base running around like this. And we're going to draw those 2 lines onto our base map now and sketch on the position of the fault. Okay, let's do that. I've got a pen. The orange I'll mark for the top of the escarpment, the blue for the base, and we'll use the pink just to track on as we go. So there we go, that's its pattern on the base map. So let's continue and change the view, and we're going to track this fault further along. So I've changed the view now, and we can see we've mapped it to here, and here comes the fault further around here. The top of the fault, the amounts of the footwall cut off of the basalt, and then the base of the escarpment running around in here at the foot of this slope where these units come down. So we continue to map the fault on. So I'm just going to draw this now onto the base map again. So a little more of the fault plane mapped on. Now let's just briefly look to this part of the image here. we can see that we have another little escarpment here that runs up and joins the one that we've mapped so far. So let's put that now onto the map. So we have a branch point where the two faults merge. The first fault up here and the second fault. And we're going to go on now and consider this area up here. And the combined single fault comes to another place where it splits. So let's spin around to look at this splitting pattern. And we see the main fault come up here and another one below take over. So another place, another branch point beyond which two become one. And we can compile this onto our base map. So we've established that faults could branch together and we've tracked that now by mapping them out onto our base map. Now let's move to the next fault further in to this system, and we can see there's another fault coming across here in this position here. So let's just trace this out. So here's the top of the next escarpment. There is the escarpment, there's its base. So this is the fault. So we'll trace this in this direction. We come across this river gorge through here to the next continuation of the same fault. To the end of this sandy area. And on to here. So I'll just tip it up. And there goes our fault. Quite sinuous, isn't it? But a continuous fault plane running across the landscape. And again, let's just transfer that information onto our base map. So we've found faults that can branch, and we've also found a fault that's long, and we can trace it out through many kilometres, but its trend doesn't have to be straight. It can change strike and be very sinuous, creating this shape in the landscape. We'll try and understand why that is shortly, but let's find another relationship, and we're going to move to this area here, a little bit further over, systematically making a bit more of our map. So here's the fault we've just mapped, the long sinuous structure with the gorge cutting through it. And now here's another fault, and notice that it comes along here and runs out into this area of sand. Conversely, there's another fault here that comes along and runs down here to be lost in this braid plane. And there's another fault here behind that sand that comes along and is lost into this area here. So we've got evidence now that faults can terminate, not join, but terminate. So again, let's compile that information onto the base map. These areas here where one fault overlaps another, and indeed another, well, these areas of overlap are called relay ramps. They're defined by the termination of one fault and another fault. The terminations, of course, are fault tips. And we can see that as we follow one of these fault scarps along, it gradually loses height towards the tip. It's true for this one, true for that one, it's true for this one here at the back. So the escarpment height, which is a representation of throw, our proxy for displacement, systematically decreases towards the fault tip. So it's the systematic, gradual loss of displacement towards these fault tips on overlapping faults that create these relay ramps. Okay, well, let's just trace out some of these faults and see, well, how extensive they are. So I've tracked this fault along from its tip here and the relay ramp around here, and the fault tips out again at this end. So the fault has got that length on the map. Let's transfer that information again onto our base map. So that's a fault length of about 6 kilometers. And we can see there's another fault just coming in here that's tipping out within this fault block. Let's just trace that one out as well. So this fault runs from here to here. It's got that length, again, about 6 kilometers. So another isolated fault is isolated from its neighbours, but part of the overall fault array. And again, let's just compile that onto our base map. So we built up part of our base map, getting an idea of the structure of this array of normal faults in the landscape. Well, I'm just going to go and add a little bit more to this base map, and then we can consider the pattern of the faults on a slightly more complete basis. And here then is our completed map. It's a pretty wonderful fault pattern. If we now to colour in the fault escarpments on here, we're creating a fault loss map. We've got faults that we can find that join together, diverge again. So branching fault patterns. We've got other faults that we can trace as single continuous strands through our study area, but the faults are sinuous. We've also found isolated faults that terminate with tips at both ends, and where these isolated faults overlap, here's another isolated fault, here's another strand coming in. Where we get overlaps, we get a relay ramp, another relay ramp here where this overlap occurs, and yet another through-going long sinuous fault at the back. So a range of different fault geometries and connections in this area. Well, the key to making a successful fault map is to work systematically, tracing fault by fault in turn, gradually building up the map in strips, and then turning your attention to the pieces between the faults, the fault blocks, and finding the isolated segments in there. And we can compare our pattern from here, from the landscape from Djibouti, with examples from the subsurface in other parts of the world in sedimentary basins. Fault loss maps for the subsurface, created from seismic imagery, show similar sinuous, frayed fault patterns, where some faults are isolated, others join and branch, and others create relay ramps. So now we've studied the fault pattern and mapped it out, let's maybe think about why we get sinuous faults like this one here that we've just mapped. Well, perhaps these are formed by shorter fault segments joining together, and because the segments didn't quite line up, the amalgamated structure is sinuous. Well, of course, we can take this exercise much further if we wanted to and look at these fantastic depositional systems operating within this tectonic landscape. So we can trace the drainage coming through the fault blocks, connecting through this gorge that connects one braid plane with another. Interesting, this half-graben changes very dramatically from braid plane deposits to this sandy material which is in this dead end to the valley system in here. So ponded sand here, and we can see a similar ponded sand in these little half-graben on the isolated faults and also in the relay ramp area up here. So really spectacular depositional systems in this tectonic landscape. But that's for another day. Of course, these really wonderful tectonic landscapes have been surveyed in great detail with really high precision to quantify the heights and variations in heights of fault scarps. It's not really what we've been about here. Rather, we've been working at a scale and with a precision that's more directly comparable with that we can resolve in the subsurface using 3D seismic surveys. So although this is an exercise that works in its own right, it also is a really great way to build confidence in students beginning to learn about the structures that we find in sedimentary basins and take understanding of fault networks into their interpretations of 3D seismic. Well, there's a formal write-up of this exercise in a special publication of the Geological Society of London on geological mapping, and you can find the reference for that in the text at the bottom of this video. Well, I hope you have a go at this exercise. It's really good fun, and it's a great way of exploring this really wonderful tectonic landscape.